All right, good morning, everyone. I'd like to thank everybody for joining Rumsey on our ongoing Locked In series hosted here by our Rumsey specialists. Introduce myself. I'm Sean Huber. I'm one of the Automation Systems Group's managers here at Rumsey. And today we're going to continue focusing on the power side of our business with a presentation around installation considerations for the modern VFD. So all that being said, I'd like to introduce Jared Roberts. Jared's one of our Rumsey Drives power specialists. He typically resides in our Bethlehem office when he's not locked in at home. He's helped me out personally and many of our customers over the last 7 years. Everything that's involving low voltage drives for Rumsey or medium voltage drives plus motors and any of the associated pieces and parts that go with all of that. So with that, Jared, I will let you take it over.
All right, thank you, Sean. Hello, everyone. My name is Jared Roberts. I am one of the drive specialists with Rumsey. I've been with Rumsey for 7 years, and prior to that, I spent some time supporting a different manufacturer's product. Today, we're going to go over many of the installation considerations required when installing a drive system. When we refer to drive system today throughout the presentation, we're not going to be referring to a coordinated system with multiple drives and motors, but rather the power distribution to the drive, to the motor, or a line to load. So Rockwell spends some time and actually monitors customer problems and issues. What they found was a pretty large percentage of issues that customers were experiencing were directly related to improper installation or environment that the drives were actually installed in. What they realized is that many customers are not designing, installing, or maintaining their drive products correctly. So today we're not going to try to solve every particular drive problem, but what we're going to do is we're going to go over some of the guidelines and best practices for looking at the entire system to make sure that we actually properly install the drives and hopefully prevent a lot of the issues we're going to talk about today. So perhaps some of these issues look familiar. You may have seen them in your facilities where customers have these same issues. Basically, I mean, we could have problems arise as a fault on the drive itself, pretty straightforward, or improper installation can result in affecting actually other pieces of equipment external to the drive itself. If we take some time up front and look at the overall installation, we can eliminate a lot of these problems from occurring. Throughout the presentation, we're going to reference a number of different manuals. Rockwell does a great job and has a bunch of information that's available free for download at their online website, the literature library. So at the top of the page here listed are some product-specific documents, the PowerFlex 750 series drive installation instructions, and the 520 series drive user manual. Again, those are specific to the products. When installing a drive, we want to reference those. Listed below are actual documents available from Rockwell that aren't product specific, but they have key guidelines to reference when making any installations on any variable frequency drive products. So not just Rockwell drives, they could be used for a third-party manufacturer as well. So here we get basically to the main topic or part of our discussion today. We're going to go over the three main parts that make up the drive system. Those are the drive input, the drive panel, and the drive output. We're going to basically cover the necessary recommendations or considerations to make in each specific part, and also discuss some of the problems that can occur if we're not careful. As I mentioned earlier, today's presentation is going to be more of a basic overview. So I wanted to bring to the attention of everyone that later on we're going to have upcoming webinars that go into more specific detail on particular parts of the drive system. So, for example, here later on this month, we have one specific to the input of the drive called line side protection, and later on in May, there's one for the output called protect your motor. So, when you have a chance, get yourself registered to attend those as well. Okay, so starting off with the drive input, the first area of consideration with the power distribution, we want to determine the source impedance. Okay, so if we look at the wiring and grounding recommendations manual, drives IN001, there's actually tables that we can look for the specific drive type and determine what the maximum allowable kVA, supply kVA of that transformer is. So if we look at the table for our particular drive, we can see if our transformer that's supplying it is larger than what is listed there, we're actually going to need to add some type of impedance, and particularly we would add a reactor. In this case, the column to the right of it actually gives you the part number for the required reactor for your drive. So some things to take into consideration here. We want to make sure, obviously, we determine what the source impedance is. Also, if you have an application already and we're experiencing input failures on drives or overvoltage or undervoltage faults, it could be a good indication that we need to have a reactor out there to prevent and protect, provide some buffering, help with line sags and spikes. So in addition to the source impedance, or looking at the kVA tables as a reference, there may be other circumstances where it might be a good idea to have a line reactor out there on the input of the drive. This lists some examples, just a few of them here. Power factor correction capacitors, if they're in the system, you're aware of them, might be necessary to add a reactor there. Also, if you have and know of a voltage imbalance, you're going to be installing the drive in, be another good example. Okay, moving on the input here, we want to make sure we determine what the actual grounding scheme is of the power distribution, right? So we want to determine what type of grounding is actually being used. Rockwell is kind of unique in the fact that it can actually support and operate on multiple different grounding schemes. For example, here, a solidly grounded system. It can also accommodate high resistance ground and ungrounded systems. Not all other manufacturers can actually do that. Either way, we want to make sure that we understand what the power distribution grounding system is, and make the rest of the necessary adjustments for acquiring the proper grounding in order to basically avoid any equipment damage or overvoltage or ground faults to occur. So the recommended grounded type or grounding scheme to be used will be a solidly grounded system. This is going to be the most reliable solution, and also it's the only system that's really CE compliant. So not only is it important to make sure we have a properly grounded transformer and we understand what type of ground system is being used, we want to follow the proper grounding schemes throughout the rest of the system. So what this diagram is showing is that the motor ground, the drive ground, and the transformer ground are all connected at some point. And this does a good job of containing the common mode noise that is created by the drive, and gives us a clean ground grid. So in addition to making sure we have the proper grounding, we also want to make sure that the drive itself is configured correctly to operate on the system that is being installed in. So on the left-hand side here, there is a table that is from the PowerFlex 750 series installation manual. It actually shows a chart that on the left-hand side lists the power source type, and then the two columns to the right actually show and recommend which position the PE jumpers or power jumpers for the drive need to be installed in according to those power source types. Failure to do this can result in actual damage to the drive or ground faults occurring. So it's really critical that this is taken into account. And oftentimes it's overlooked because it's not really easily seen. In fact, Rockwell has gone to the trouble here to ship the drives with a sticker that specifically states to confirm the position of these power jumpers prior to powering up the drive. So again, another critical aspect here, making sure we have the drives configured correctly for the install. Here's an example of a solidly grounded system. On the left-hand side, we have the drive without that PEB jumper installed, okay? So we can see voltage spikes on the DC bus are exceeding 1,000 volts. On the right-hand side, we have the same drive, solidly grounded, with the PEB jumper installed correctly, and we can see that the voltage spikes have been decreased and peaks are below 500 volts now. So again, critical to make sure we have the drive configured and installed correctly for its system. So another thing to note on the PowerFlex 750 series, we were referencing and talking about these position of the power jumpers. It's actually possible to determine basically the way the drive is configured from the factory by looking at the catalog number. So on the left-hand side here, we see the catalog string, and based on its configuration here, we can see if the jumper is installed or removed by default from the factory. On the right-hand side, there's an image from the configuration tool just showing if we want to have a drive shipped from the factory with the jumper installed, we would have the J in the part number, and that indicates, again, the power jumper is installed from the factory. When we receive it, it should be in the installed position. So moving on to the drive panel, there are many atmospheric and environmental considerations that need to be made when installing a drive in a panel. I think one of the most common or easily understood is ambient temperature. So if the temperature of the air surrounding the drive exceeds its ambient rating, we're going to expect reduced life or over temperature faults to occur, and that's pretty common with any electrical component. But what is most often overlooked is the minimum spacing requirements. And on the lower left here, we have an image from the PowerFlex 520 series installation manual or user manual. And it clearly states that the drive needs a certain amount of space above and below the drive. And the main reason for that is to provide adequate airflow. So if we have anything in between or closer to the drive than what's recommended, basically what the result is, we're going to end up restricting the airflow. And airflow is the most critical part for providing cooling for the drive. Another consideration for the panel is the environmental or atmosphere which the drive is installed in. We want to make sure certainly that we're not exposing the drive to a lot of dust or corrosive gases in the environment. So we want to make sure that we're taking all the proper considerations to make certain the drive is protected against its environment it's installed in. One of the things to add reliability is that Rockwell makes sure all of the boards on the PowerFlex drives are conformally coated. Okay, so another resource for industry-specific considerations for atmospheric requirements is the drive's AT003. That's a good reference that we can look at when we're installing our drives in specific industries or applications. We can look at that resource to see what is recommended for similar installs and situations. Moving on to the drive panel, again, as noted earlier, grounding is important. There's no difference here in the panel. What we see here is improper grounding practices often result in some nuisance issues, whether it be ground faults or communication issues. Many times the motor ground isn't tied in correctly. What we'd like to see is the motor ground coming back from the motor. The leads should go directly back to the drive and then to panel ground. And that goes the same for the shield as well. So the shield and the motor cable should go directly back to the drive before going on a separate cable to the panel ground. One way to ensure that the proper grounding methods are followed is trying to make sure that our wiring diagrams properly illustrate the correct grounding methods. So here's an example of wiring diagram. We can see here the motor, ground, and shield going back to the drive, and a separate ground that goes in over to our panel. Again, just good to enforce that we do the proper grounding. So here's an example of improper grounding causing an issue out there in the field. So we actually had a motor ground coming back into the panel and actually tied to the common panel ground before then eventually routing back to the drive. And what the result was basically intermittent issues that caused a stoppage on the machine. They were losing the disconnect input and some operator safety mat inputs as a result of the improper grounding here. One other thing to note in the panel for drives is the use of a back panel. Rockwell actually recommends using a galvanized panel to mount the drives to. It's in order to basically prevent or present and allow for a better grounding point. This is a better object or solution than using a painted panel, because many times the painted panel you're going to have to actually remove the paint at any mounting point or grounding point, and also it opens up area for corrosion to occur.
Jared, if I can just jump in real quick on that one, I want to double kind of stress the galvanized back panel use. I know sometimes we tend to get looked at a little funny because everybody likes painted panels, but high frequency noise tends to like surface area to be gotten rid of, as opposed to safety ground, right? Which is a point solution. So not having all of the paint on a galvanized panel does a few things for you. One, around noise specifically, but also, even just heat transfer out of the back of a drive if it's mounted to it, and other things that can significantly benefit you. One of the reasons that I bring it up so strongly is because of, working with servos over the years, kind of falls into the same things as drives. And, galvanized back panels are readily available now, and just a better way to move forward if you're building panels, especially since most panels are so packed you can't see them anyway, so you really can't tell hardly if they're galvanized versus painted. Thanks, Jared.
Yeah, thank you, Sean. So moving on to cable types, there's really only two cable types that should be considered when using a VFD. A shielded cable does a good job of containing the common mode noise, and also helps to prolong the life of the motor. In situations where you may need some more mechanical strength or resistance to moisture, may want to consider using an armored cable. Okay, so moving on to the output of the drive. One of the most common field-related issues are due to the motor cable lengths themselves, and what we see commonly are motor failures or overcurrent faults. In the drive's wiring and grounding guidelines, the drive's IN001, there's actually tables available for your specific drive that show the maximum allowable lead length for that motor, okay, or between the drive and the motor, basically. All right, so based on the columns shown in this table, we can see what the resulting voltage peak is for each different lead length. Okay, so we can determine if a reactor is required for however long our distance run is to the motor, if we need to add a reactor or a DVD-T filter, for example. One additional thing to note here is that cable charging currents are not taken into account on this table.
So Jared, if I had a motor and looking at that chart, how would I know whether something's 1,000 volt versus 1,600 volt rated?
Okay, so so really this is going to indicate, what that peak, the voltage peak is based on the wavelength, or the lead length rather, and if you needed to determine what your insulation rating on your particular motor is, the best way to know for sure would be to, consult your motor manufacturer. Another way, I mean, if we have for instance, an MG1 rated motor or inverter duty rated motor, we can know that that's a 1488 voltage rated motor. If it's design B, it may be 1200 or 1000 volt. So again, if you're not aware or sure, it might be best to convert or consult the motor manufacturer. Again, moving on to the cable type or types of cables we discussed earlier. It's also, in order to avoid overcurrent faults or ground faults from occurring, important to look at the actual construction of the cable and the rating of that cable. So based on our installation and what drive size and what we're doing in that particular application, we're going to need to use a specific rating cable. In the drives guideline manual, there's tables that basically instruct you on what type of cable to use for that installation. Moving on to cable charging currents. Most times we see smaller drives that are susceptible or most susceptible to the cable charging currents, typically 2 horsepower and under. On the left-hand side here, we see a relatively short lead length of 3 meters between the drive and the motor, and we can see the output waveform. On the right-hand side, the motor lead length has increased to 30 meters, and we can see the resulting current output from that. Basically, in some cases, especially when we have smaller drives, the cable charging currents can be greater than what the current rating of the drive is, and we can experience overcurrent faults on the drive. So in order to eliminate that up front, if we know we have an installation and the lead lengths might be getting kind of far, first thing maybe to be considered would be how can we shorten those lead lengths if at all possible. Another thing we could do would be to slightly increase the rating or size of that drive from the start. Also, we can lower the switching frequency.
And Jared, we do have a question here. If the wire's running through some type of metallic conduit, the question says, do you still recommend running cable? Or maybe, I guess, is there some consideration if you're running through metallic conduit?
So yes, it's actually one of the most important considerations there would probably be to make sure that you're following the guidelines and not routing too many cables in the conduit. So you're using the proper size conduit and the right amount of cables. And then, yeah, the shielding could come into play there as well, especially for capacitive coupling. So, yeah, a good factor.
So I can jump in there a little bit, Jared. Just so from a reference standpoint, you're not allowed to, if you're just using standard cables, non-shielded, you're not allowed to have more than 3 sets of motor leads in one conduit, or you will get crosstalk and you'll get voltage, kind of passing between the cables, and you'll definitely notice that. So there is guidelines within the installation of no more than 3. I know sometimes the question comes up of, do I need shielded cable inside conduit? Typically the answer there has historically been no. But I will say that shielded cable is, obviously it's generally a better, like a lot of Rockwell's references are Belden cables, and they are a very well made, product compared to standard like THHN or something along those lines. So there are a couple of guides and specifics around that you can get into depending on your installation.
Thank you, Sean. I guess so. The question was specific to, do we need shielded cable when we're running in the conduit? Was that correct?
It's a combination of maybe both. I probably added in a few extra things there.
All right. So another thing to consider inside or as far as the output of the drive and as well as the inside the panel would be, and it's very frustrating if it's ever occurred to you, intermittent comm faults and I/O loss of signal can occur when we don't properly route the the power output cable or have the drive components or power components separated from our sensitive equipment. In the diagram here at the bottom basically shows all of the power components, the drives, and their power cabling routed on the far right-hand side of the enclosure and kept away from any of the sensitive equipment and the control wiring. And again, we want to try to do that whenever possible to keep from inducing any of the noise created by the drives into the rest of the equipment and our control signals. One other thing to help eliminate and mitigate noise created by the drives would be the addition of the common mode cores. The drives guidelines has documentation in there that explains specifically when we might want to consider adding the cores and also how to go about properly doing so. Okay, so common mode chokes are effective at reducing common mode current that's created by the drive. Drives use pulse width modulation to control the speed of a motor. That rapid switching of the voltage on the output creates a current form that looks similar to what we see in the middle of this chart. When we add the common mode choke, it effectively dampens the peaks and the ringing from that waveform as we see at the bottom. Okay, other things to keep an eye out for, if we're using an encoder, we want to make sure we're using the properly rated encoder cable and shielding, and that it's actually routed in the correct manner to prevent bringing any issues or presenting any issues for us. Another thing, noise related, would be using the properly rated communication cables and routing those accordingly as well. I know Rumsey has the properly rated comm cables available when you're doing an installation to make sure you're not bringing any noise into your system. Okay, so we covered a lot of the main considerations and areas in the drive system where to look, and we also provided a bunch of resources as far as documentation to use to arm yourselves with all the necessary information you need when you're looking at an installation. The biggest thing here is, whether it's a new or an existing install, to make sure we take a look at the whole system anytime we're going to try to work on or change anything in a drive system. Okay, so I mentioned earlier we have some related upcoming webinars. So if you can get yourself registered. Also want to make mention that there is a MCC specific webinar coming up later in May. And if we have any customers out there listening that have MCCs or want to know about MCCs, feel free to register for that one as well. So thank you.
And Jared, one comment that I would like to add in. I know you had mentioned it, but I don't know if everyone would have picked up on it back kind of on the output section. But you had mentioned about PWM or carrier frequency, as something to consider. And that is basically the pulse width modulation. So it's the rate at which drive recreates the sine wave out to your motor. Most drives now, and that's what you hear. So everybody, when you turn on a drive, whether it's a VFD or a servo, you hear that whine. There's a lot of problems that can be fixed by adjusting that frequency. So depending on the size or the horsepower of your drive, it'll come in a lot of times. The carrier frequency will be 4 kilohertz. The larger the drive, they'll come in at 2, or it's possible sometimes to set them up as high as 12. When you start setting them to the higher frequencies, it is possible to start inducing higher noise related issues into your system. So the main thing I wanted to do is just kind of point out that there is a setting within every manufacturer's drive, at least at the best of my knowledge, for that. So if you start running into some very strange things where you run into some nuisance trips on the drive, or you see output modules, PLC output modules blinking randomly, things like that, sometimes the easiest thing to do is to change that modulation frequency. beyond even just adding the common mode cores and some of the other things that you can do to help alleviate it. So I just wanted to throw that out there as kind of one of my personal pet peeves, because we've fixed many a problem over the years, and it's not one that comes up a lot of times when talking to support. So yeah, so anything else other than that, Jared, as far as just an overview?
Well, I think that's it for the most part. Do we have any questions?
We do have a question that came in on the chat, Jared, and it says, "Do chokes prevent the damage that shaft grounding rings are used for?"
Jared, opinions?
Okay, so yeah, one of the culprits to premature bearing failure in the drive is the result of the common mode noise that is created by the output of the drive waveform. So yes, if we use the common mode choke and effectively eliminate the creation of the common mode current at the drive source, it can help protect the motor on that end. Correct.
Yeah, and I will say that that motor issue, as far as the discharge through the rotor to the stator and going through bearings, has been an age-old problem ever since IGBTs came out. And there are a lot of different ways to try and help alleviate that. From, I'm sure most people in the call have heard of Aegis rings that can help you ground it, or just ground brushes. But some of the best things that we've seen to help solve those issues is just good grounding practices. So when Jared showed that overall best grounding, we've seen a lot of installations where the PE is brought back directly from the motor to the panel, and then from the panel up to the drive, and over time there's corrosion and things that occur, and you start getting some pretty strange things occurring. So following that guideline for installation is very important. All right, so then Jared, we have another one here. If we modify the shape of the sine wave from the VFD, what other effects could we have on the motor? Do you know what would be meant by that, Jared?
I'm not sure I understand exactly. I mean, there is some considerations to be made in general for any motor when we're operating on VFD power. I mean, the best recommendation would be to make certain that it's actually rated for VFD power, where it being a VFD rated motor. But there are other things you can check with the motor manufacturer to make certain that what the operating range is, the speed range of the motor for variable torque or constant torque loads. Make sure that the motor has sufficient cooling. So there's a number of different factors that we would consider to make sure we protect the motor in an installation.
Yeah, I mean, the only things that I could maybe add in there a little bit, Jared, is that there are devices on the output, and we'll go into those in much greater detail in the other presentation, or the next presentation, that can help with recreating closer to a sine wave on the output, so that you can have motor lead lengths that it doesn't heat up the motor as bad, so your motors last longer. But generally speaking, on a 480 volt or 460, 480 volt drive, you have a 780 volt bus, and all you're doing is spiking out from the IGBTs, turning on and off that voltage. And so based on how that's working, you're changing obviously your frequency, which is what's controlling the speed of your motor. I'm not aware of much else that would truly change that. So feel free to contact us afterward if we didn't answer your question entirely. Definitely can talk through that a little bit more detail.
Yeah, and to your point there, Sean, we referenced the motor lead length tables earlier, and we mentioned that peak voltage on those particular lengths. So, that's really referring to the voltage doubling phenomenon there, or effect with the DVDT. You have those voltage spikes that occur due to reflective wave that could damage the windings on the motor. And like you mentioned there earlier, that Protect Your Motor webinar should go into more detail on that one as well.
And I'll just add that John McClavick, one of the power specialists from Rockwell, just put a note in there as well that a motor is designed for specific voltage and frequency shaping, if you will, that the volts-hertz relationship can add, and that can add heat to the motor. So I didn't know if everybody saw that in the chat there. I think
All
you have
right.
a few other questions
Yeah,
there,
a few
Sean.
other. Another one is, are there circumstances where you do not want to use line reactors before and after the drive?
So on the output, I know sometimes we can actually reduce the voltage output. So if you're already actually in a low voltage or a lower voltage to begin with, and you don't want to reduce it any further, it might not be a good consideration to have the output reactor.
Yeah, on the input side of the drives, kind of the same thing that Jared just said there, that if you had to worry about low voltage, but generally a line reactor doesn't take up much, you don't lose much on the voltage side. The only time that I've seen any issues on the output side of a drive is if you're trying to take one of our newer drives like a 755 or something and control servo motors with it, or very, very tightly controlled, paper machine type applications. You won't be able to tune the drive and the motor as tightly as if you didn't have a line reactor on the output. That being said, every other application, fans, pumps, all the normal things that are out there, the line reactor will actually be the first inductance that those spikes hit and start to smooth out. So the line reactor will get hot, which is better than your motor getting hot. So I would say in general, if you have the space and you have the money, an output line reactor typically is helpful for the longevity of the motor. And then let's see, there was one other one here, a couple other ones. Does a low kilowatt single phase drive need a line reactor or choke? Jared, any thoughts on that one?
Not really.
Well, it's Rick. First, we need to clarify single phase. We don't have a single phase output drive. If I believe it's Devin is asking, you're talking about a single phase input, three phase output.
So we'll make the assumption yes, because we don't have a single phase out. Go ahead, Rick, or did we lose you? You're muted.
I'm here. Single phase reactors are available. We don't run into them that often. I'm going to have to look in the drive's installation and see if they even have anything referring about any recommendations on that.
Yeah, when to even install them when necessary. I mean, typically, whatever's feeding the single phase would be relatively small as far as transformers to begin with. But yeah, we can certainly look into it.
Yeah, I had a few applications that I've had to take you actually use a three-phase reactor and you put it through the L1, L3, or L1 and L2 side and can put impedance in front of it if needed.
Okay, so hopefully that answers it for you, Devin. If not, feel free to reach out to one of us. We'll definitely help you out on your specific application. All right, I think that's all of the questions that we have popping up. So I guess with that, I would say, thanks everyone for tuning in today. If you have any questions specific to this topic, feel free to reach out to, Jared, whose information here, or any of the specialists on our team. Don't forget that we have a bunch more of these tech talks coming up through the end of May, every Tuesday and Thursday. I think our one coming up this coming Thursday is specific around motor fitment. So it'll kind of tie into the power and some other associated things. We will get out to everyone a recording and all the supporting information, and we will talk to everyone soon. Thank you.